Hey everyone, Simplified Engineer here. Today we're going to be looking at a horizontal Venturi meter flow measurement using Bernoulli's principle and continuity. For this example, the given parameters are d1 equals 0.2 meters, d2 0.1, and our delta P over this interval is 15 kPa. We're going to be looking to find V1, V2, and our volumetric flow rate through this measurement. So we're going to be starting out here with the continuity equation, and this is A1V1 equals A2V2, and we know the formula for area is pi over 4 times your diameter squared. So we have D1 here as the diameter, and when we substitute in, we're going to get 0.2 squared. And similarly for A2, we're going to be using 0.1 meters, so it's going to be pi over 4.1 squared. And we solve out for this, we get 0.0314 meters squared for A1 and 0.00785 meters squared for A2. Now when we bring this down, we can pull out V2 out front, and we get V2 equals A1V1 over A2. And this is going to substitute out. If we pull out the V1 in front, then we can do A1 over A2. And this is 0.314 divided by 0.0078 to come out to 4 times V1. So therefore V2 is going to equal 4 times V1. We can then write out Bernoulli's equation. I sped this up a bit so you don't have to watch me write the entire thing out, but this should be in the back of your textbook, or you can pause the video to copy this down from my page here. But we're going to be first looking at to cancel some elements out of this. The first one is going to be our height. Because this is horizontal, Z1 is going to equal Z2. So that's going to be 0 on both sides, and we can actually cancel out that whole part of the equation. And it looks like there's nothing else here to be canceled out. However, we can pull the pressures both to the same side, and we get P1 minus P2, and leave the rest of the stuff on the other side, which gives us a delta P equals 1/2 density times V2 squared minus V1 squared. And from the given above, we know that delta P is 15 kPa and the density is 1,000 kilograms per meter squared. This is the water density. When we substitute in, we get this formula here, and I sped this up a little bit again so you don't have to watch me write it out. But eventually, once you solve through, you'll get 15,000 equals 500 times 16 V1 squared minus V1 squared, which eventually simplifies to 15,000 equals 7,500 V1 squared. And when we solve some more, we get V1 squared equals 2, and therefore V1 is going to equal square root of 2, which when you punch that in your calculator, it comes out to about 1.414 meters per second. So that's our V1. And we know from above that V2 equals 4 times V1, so we plug this in again here. We get V2 equals 4 times 1.414, and that comes out to, let me plug this in, about 5.656 meters per second for our V2. And to find the flow rate, we get Q equals area times velocity. And this would be the same if you took this for A1V1 or A2V2. For this example, I just did A1 times V1. Looking up, our A1 is going to be 0.0314, and our V1 is 1.414 meters per second. And we put this in here into our equation. So it's going to be 0.0314 times 1.414, which gives us a flow rate of about 0.0444 meters per second. Meters cubed per second. And yeah, that about solves this problem actually. So we got the flow rate here, we got our V1, we got our V2, everything that we were looking for part of this problem. And the V2, like I said here, is about 4 times what V1 would be, which is what we did find in our equation above. And this is because our area downstream is about 1/4 of the side of the area upstream. So that is where the correlation comes between the two of them. And we do get a final flow rate here at the bottom. So yeah, hope you enjoyed the video. If this helped, drop a like and a comment down below. And if you have anything else you'd like me to look at, just drop a comment. Thanks.